welcome back to Well, That's Interesting, the New Year, New Ways to Discover Terrifying Things in Space edition. Today is episode 262. New monster black hole may be the largest so far, and it was found in a new way. And this pulsar spins 592 times per second, and that is just the beginning. My friends, call me sadistic, call me a masochist, call me an optimist, or call me a doctor for the head injury I may be suffering, because believe it or not, I'm actually looking forward to 2026. There are 52 Thursdays this year, and that means I have 52 chances to bring you the weird, the profound, the inspirational, and the stories that make you want to curl up into a protective ball thanks to the overwhelming feelings created from learning that the universe is just too fucking big, with too many big fucking things in it, doing all sorts of big crazy shit. I know, that was poetic. What I mean to say is that you and I are kicking off the very first episode with two discoveries that not only shatter records, but how they were discovered brings new methods to the table, opening up opportunities to find even more monsters out there in the great beyond. In the first half of the show, a behemoth that is one of the largest black holes ever detected, and maybe the largest so far thanks to some incredibly accurate readings. Now, if you're a long-time listener of the show, then I am proud to say you are probably well-versed on holes, especially supermassive black holes, who on one hand can untangle every molecule from every object that treads too close, yet on the other, we need to thank them for galaxy formation. Yeah, black holes help with fueling and regulating galaxy growth. It's no coincidence supermassive black holes are located at the center of galaxies. As they spaghettify every and all things within their reach, this activity can actually heat gas light years away, leading to a period of controlled star formation as that gas takes time to cool, collapse, and solidify into beautiful things like our sun, whose own mass aids in consolidating planets and thus entire solar systems. These stars, by the way, are incredibly useful, not only for creating life and shit, but for helping NASA nerds discover these holes and their gigantic proportions. As reported by Daniel Cleary of Science magazine, at the center of our Milky Way galaxy is Sagittarius A, a black hole with a mass of about 4 million times that of the sun. And although it sounds like you can't miss it, this black hole and all black holes are invisible. So astronomers, quote, deduce the mass of one by studying how fast nearby stars or gas clouds orbit it. That's how astronomers weighed Sagittarius A, an accomplishment that won a share of the 2020 Nobel Prize in Physics, end quote. Well, that's not bad. This is a pretty handy-dandy cheat. But it can only go so far. Literally. Galaxies 2 billion light years away and beyond pose a challenge. Even our most impressive telescopes can't discern the movements of stars close enough to the black hole. In these instances, hot-for-holes astronomers turn to AGN, or what's called the active galactic nucleus, which is just a fancy way of saying looking for the gas and dust spiraling a black hole, aka its accretion disk. Friction within that disk heats material to millions of degrees, causing it to radiate intensely. I'm talking everything from light to radio waves, and gamma rays can pop off. Again, if you're a long-time listener, then you know that this energy can escape as two jets, one at either end of the hole. We call them quasars, or blazars if they're pointing at our planet. And yes, I know it sounds dangerous, but if you have a listen to episode 228, our sun will eject a superflare with the energy of 1 trillion nukes, and a supermassive black hole is shooting its own beam of energy right at us, you don't need to worry, girl. All known blazars are too far away to eradicate life as we know it. And that's good news. But here's some not-so-good news. Astronomers have analyzed many an AGN to create an AGN spectrum, a table of sorts, that says if the AGN is XYZ, then the black hole's mass is probably this number. But as so wonderfully summed up by astrophysicist Carlos Melo Carneiro of the Federal University of Rio Grande do Sul in an interview with Science magazine, quote, "The method works, but it relies on a lot of assumptions. As a result, the masses of supermassive black holes in distant galaxies are known only within large uncertainties. End quote. Well, what can I say other than Carlos and his colleagues have had enough of these large uncertainties and went on ahead to create a brand new method that doesn't even take AGN into account. If you think something like this would make astronomers clutch their pearls, you have no idea. We will dive into this method. We will use this method to analyze the center of one of the most massive known galaxies, which is part of a binary set of galaxies called the Cosmic Horseshoe. I'll explain why they're called the Cosmic Horseshoe and what causes its shape. Okay, sure, you already know it's a black hole, but girl, you need to hear the staggering details. Then after the break, we're moving on from one binary system to another, a binary stellar system, which means it's made of two stars. One of these stars is a tiny neutron star, specifically a pulsar. And yes, I will be explaining what in the ever-loving Christ that is, but in the meantime, just imagine this star being orbited by another larger star, one about a quarter of our sun's mass. This sounds like an unassuming little setup, yet, of course, it's anything but. For years, astronomers saw this pulsar behaving in strange ways. On one hand, it would act like any other, meaning it was emitting radio waves. But then it would suddenly switch gears by emitting X-rays. An accretion disk would appear and then disappear, followed up by good old-fashioned radio waves once again. It turns out, our tiny star is stealing material from its larger neighbor, and this not-so-subtle thievery is putting on one hell of a show. We will learn more about what's called PSR J10230038, or who I'm going to call J10 for short, because who has time for that? Our brains will explode as we hear about its rotational speed, why it's spinning so chaotically to begin with, and where these X-rays are coming from. It took nearly 20 years to find out, but the wait was worth it. In the meantime, hi, I'm Jill Chacha, and if this is your first time listening, welcome to the flock, my dizzy business goose. To begin, I'm going to ask you to put on all your thinking caps, all while expanding your mind, because I'm dialing the time machine way the fuck back to the groovy year of 1912. We just landed in a room with a lot of books and a tiny man you may have heard of, Albert Einstein, a theoretical physicist who just came up with a crazy-ass thought. Gravity can probably bend light. This thought was scribbled on paper and then elaborated on just 4 years later, when in 1916, a little paper you may have heard of called The Theory of Relativity explained, yo girl, get this. Massive objects warp the fabric of space, and this is called space-time. Gravity isn't produced by a particular single force, but by space-time. This fabric curves in the presence of matter and is visibly distorted in the presence of energy. So, for example, if something massive is out there, and light, a form of energy, passes by it, that light is going to be pulled and stretched thanks to that sagging fabric, you dig? I think I'm going to call this effect gravitational lensing. Well, in 1924, Russian physicist Orest Chalsin was like, yeah, I dig it. I dig this gravitational lensing idea. But let me take it further. If a light source and a gravitational lens were aligned just right, an observer would see a ring of light. And for this reason, I'm going to call this phenomenon the Einstein-Chalsin ring. Thank you. Well, I can only assume Einstein was flattered, but he didn't address the ring theory until a decade later. Between the odds of that alignment and the technological abilities of the times, he noted in the journal Science, quote, "There is no hope of observing this phenomenon directly," end quote. Well, as we know on this show, never say never when it comes to nature and our ability to build cool shit that doesn't destroy things. In 1979, the first gravitational lens, a system where a heavy-ass foreground object distorts the light of a background object, was discovered. And it wasn't too long before that theoretical ring was finally found. In 1987, a team led by Jacqueline Hewitt at MIT used the aptly named Very Large Array Radio Telescope to take a gander at an unusual radio source named MG 1131-0456. And if you drop whatever very large array you're holding right now and pick up your phone to tap on today's post, you'll see what they saw. A distinctive blue oval with bright ends. What we're looking at here is the passing energy from a background galaxy being distorted by a massive galaxy positioned in front of it. The team concluded that this was the first Einstein ring, coincidentally telling Einstein to shove his pessimistic outlook. Since this initial discovery, many an Einstein ring has been witnessed. And if you swipe past MG 1131, you'll see a collage of massive galaxies gravitational lensing the smaller galaxy behind them, creating a near circle. It's super fucking cool. And this effect has inadvertently helped other geeks figure out other mind-bending things. Enter Carlos Milo Carneiro of the Federal University of Rio Grande do Sul. Carlos's obsession is dark matter, an invisible substance that does not emit, absorb, or reflect light, but we know it exists because this matter interacts gravitationally with objects around it. Thanks to this scant evidence, we know, 1, dark matter composes at least 27% of the entirety of the universe, and 2, the bit of gravity it creates is actually the glue that holds together all the shit we can't see. Carlos loves these rings. And that's because their distortions are like pinpoints, revealing the distribution of matter within the foreground galaxy and thus where the foreground galaxy's dark matter is located too. Now, needless to say, when you're looking for something practically invisible with Einstein rings as a guide, it helps to get the biggest damn ring you can find. And the biggest damn ring out there, known so far, is the cosmic horseshoe. Please, 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 drop whatever bullshit you may be holding right now, and yes, pick up your phone. I have a photo of the horseshoe, and yeah, it really looks like a beam of light in the shape of a horseshoe. In the middle of that shape is an orange ball of light. And guess what? That is galaxy LRG 3757, one of the most massive galaxies ever observed by astronomers, having a mass 100 times that of the Milky Way. It sits approximately 5.6 billion light years away from Earth, but a smidge closer than the galaxy behind it. So, if you're thinking, that horseshoe must be the light from the background galaxy bending from the mass of LRG 3757 in front of it, you are correct. As Carlos and the gang went ahead with their clickety-clack calculations and mapping of 3757's mass distribution, they eventually got to its creamy middle, which wasn't creamy at all. It was void of light and unfathomably dense, which can only mean one thing: a black hole. Now, although Carlos and the gang were hot for dark matter, girl, you know a good astronomer can't pass up the possibility of discovering a good hole and its mass. But the one here, well, it was going to be quite the challenge. This particular black hole, if it was there, had no accretion disk, meaning it had already consumed all of the closest material around it. So this means no AGN reading could be made. Remember that chart I brought up in the intro? The one that says if the active galactic nucleus is XYZ, then the black hole's mass is probably this number. Well, alas, the old AGN method can't be used here. The team would have to hitch up their pants and take matters, no pun intended, into their own hands. And I have to say, they weren't fucking around. I think even if they could use AGN, I don't think they would. Fitting for one of the largest galaxies out there, the team brought out the big guns, the Hubble Space Telescope, and the multi-unit spectroscopic explorer spectrograph. You know the one, in Chile's Atacama Desert? Yeah, that one. With these, they focused on the cosmic horseshoe using a two-pronged approach that has never been done before, a combo of stellar kinematics and gravitational lensing. Now, what the fuck is stellar kinematics? Don't worry, I've got you. This is the fancy term for the other method we brought up in the intro, using the stars within galaxies and the speed and the way they move around black holes. As reported by Daniel Cleary of Science magazine, although this technique doesn't usually work at such a distance from Earth, the mass they are circling is so tremendous that its gravity is whipping up stars to such a high velocity it can be detected from here. Using that fancy pants multi-unit spectroscopic explorer spectrograph, the team was able to detect the spectrum of light from each pixel in the images that they took, and that revealed how fast the stars and gas were moving around the black hole. As we fucking speak, they're moving at a vomit-inducing 400 kilometers per second. And to put that into perspective, the Earth moves around the sun at an average speed of about 30 kilometers per second, which is about 67,000 miles per hour. So we're talking over 10 times as fast. With this ridiculous statistic, the team was ready to move on to their second step to determine the black hole's mass, using the horseshoe itself. So, after mapping distortions created by 3757's mass distribution and taking into account the motion around the black hole, what did the team's computer model come up with? Drumroll, please. Thank you in the back. This fucking monster. This black hole has the mass of about 36 billion suns. 36 billion. And with an uncertainty of about 35%, this makes it one of, if not the largest and most accurately read black hole ever discovered so far. Now, I can see your reaction from here. It says something like, Jesus. You're right. That is truly big. But you know what, Jill? I'm hot for holes myself. And I know about Ton 618. According to other hot for holes enthusiasts, this black hole has a mass equivalent to about 66 billion suns, which is almost twice that of the cosmic horseshoe. So why is everyone freaking out about this thing? Well, great question, my lanky business goose. Beloved Ton 618 is 10 billion light years away, and its size has been estimated using AGN, an analysis of its brightness, and other theoretical models. As such, that 66 billion comes with a larger uncertainty. Perhaps, with gravitational lensing, astronomers can solidify and or adjust that 66 billion number for more accuracy. In fact, this method can be used to detect and measure the mass of ultramassive black holes across the universe, ones active like Ton 618, or those hidden and completely silent, just like those inside galaxy LRG 3757. As to how this newly crowned behemoth got so large, that's currently the question. 3757 is massive and very much cosmically alone out there, suggesting at some point, or at many points, there were galactic mergers. Or maybe its black hole went on a gluttonous spree, inhaling many of its surrounding stars early in its life, which I understand. But, rather going by vibe, astronomers expect to find answers with the brand new Euclid Space Telescope, which is already 1 year into its 6-year mission. As reported by Ben Turner of Live Science, Euclid has the burdensome task of cataloging a third of the entire night sky by capturing thousands of wide-angle images. Quote, all told, Euclid will capture light from more than 1 billion galaxies that are up to 10 billion years old. Once this is done, astronomers will use Euclid's images to create 2 maps. One composed of many other Einstein rings, and the other showing shock waves called baryon acoustic oscillations. These maps could help researchers trace dark matter and dark energy, mysterious components of the universe, believed to make up most of its matter and cause its accelerating expansion. The Euclid mission is expected to discover hundreds of thousands of lenses over the next 5 years. This new era of discovery promises to deepen our understanding of the galaxy's evolution and interplay between regular matter and dark matter components. End quote. Well, I bet Carlos is over the fucking moon about this. Stay tuned for more. After the break, we're leaving the ginormous hole. Sorry. We're leaving a ginormous hole for a star. That's making headlines in its own unique way. Theft, dizzying dance routines, explosions, blinding light, and missing links are next. So, you should stay tuned.
The new year brings new health goals and wealth goals. Protecting your identity is an important step. Your info is in endless places that could expose you to identity theft, leading to lost funds. LifeLock monitors millions of data points per second. If your identity is stolen, our restoration specialists will fix it, guaranteed, or your money back. Resolve to make identity health and wealth part of your New Year's goals with LifeLock. Save up to 40% your first year. Visit lifelock.com/podcast. Terms apply.
Oh, it's such a clutch off-season pickup, Dave.
I was worried we'd bring back the same team.
I meant those blackout motorized shades.
Blinds.com made it crazy affordable to replace our old blinds.
Hard to install?
No, it's easy. I installed these and then got some for my mom. She talked to a design consultant for free and scheduled a professional measure and install.
Hall of Fame son.
They're the #1 online retailer of custom window coverings in the world.
Blinds.com is the GOAT.
Visit Blinds.com now for up to 45% off with minimum purchase plus a free professional measure. Rules and restrictions apply.
And we're back. We are so back. And my friends, I owe you an explanation. At the top of the show, I mentioned pulsars, and that they fall under a category of celestial objects called neutron stars. Now, if you're a long-time member of the flock, or if you joined us back in July of last year, then you may have had to listen to episode 241. Let's talk about these two planets disintegrating before our eyes, and this zombie star moving through the galaxy at 110,000 miles per hour. Not only did we learn that solid rock can vaporize under hot enough temperatures, my God, but we also spoke about what neutron stars are and how they form. I'm actually going to quote myself here as a refresher for y'all, and honestly, hearing this the second time around will still leave you fucking amazed that these things exist. It's wild. So, here I am, quoting myself. Quote, "When stars that are way, way more massive than our sun run out of hydrogen fuel, a beautiful hell breaks loose. After fusing heavier and heavier elements, a star's core collapses under gravity, triggering a shock wave that travels outward. The shock wave heats and compresses the outer layers of the star, causing that to explode at incredibly high speeds, aka a supernova. What remains can be one of two things: a good old-fashioned hole, meaning a black hole, or a neutron star. And it's equally as insane. A neutron star is basically a core of only a few miles across, but it contains 10 to 25 or even more solar masses, meaning 25 suns are stuffed into a space only 10 to maybe 20 miles in diameter. As a visual, the island of Manhattan is 14 miles long. So how the fuck do you compress all of that mass into such a tiny area? Well, everyone, please imagine an atom. Thank you. At the center of the nucleus, there are protons and neutrons, and swinging around them are electrons. Everyone is happy and has elbow room. Now, it just so happens this imaginary atom is in a star that's about to pop off and become a neutron star. My friends, the core's collapse is so intense, the extreme pressure causes the electrons and protons to combine into additional neutrons, and that space between them is removed. According to the wiki, surpassed only by black holes, neutron stars are the second smallest and densest known class of stellar objects. A fucking teaspoon of neutron star material would weigh 4 billion tons on Earth. So please, don't take any. Oh, and guess what? There are 3 varieties of neutron stars. That's right, 3, each fucking crazier than the last. If you head on over to today's socials and swipe through today's post, I've got a handy-dandy graphic from NASA about our kooky collection." End quote. Well, good news, my charismatic business goose. I have that same handy-dandy graphic for you to look upon right the fuck now. And of the 3 types we're going to cover today, is the one dead smack in the middle there. And it's called a pulsar. And here are some fun facts about our extremely dense friends. 1. As the time of my writing these notes for this episode in late October of 2025, about 3,400 have been discovered, each detected by their pulsating radio waves, emitted similar to a lighthouse beam sweeping across the sky. Well, if that lighthouse had a beam coming out of both ends. So yes, pulsars emit radio waves from either pole. And that's not the only fun part. 2, they spin with absolute abandon. As reported by Rachel Cortland of New Scientist, your average pulsar rotates just a few times per second. But some spin hundreds of times per second. And there's a few theories as to why what's called millisecond pulsars behave this way. As the star's core collapses, its radius decreases, causing its rotation to speed up, similar to how an ice skater spins faster when pulling their arms to their chest. The collapse itself is a process that can happen quickly. And I mean it. Sometimes within tenths of a second. And that enormous amount of energy from the collapse can create a shock wave, contributing to the pulsar's spin. But there's also a possible third element, or a binary situation, if you will. Sometimes a star has a companion, and that leads to an equally enormous amount of drama. Some astronomers believe that a neutron star's intense gravity ends up siphoning its neighbor star's material. And during that process, it also transfers angular momentum to the pulsar, which makes its rotation off the charts. However, if this was the case, we would see some evidence, including an accretion disk spinning around the neutron star as that material accumulates. And this material would most likely interfere with those radio waves popping out. This binary situation has never been witnessed, up until 5 minutes ago. And this revelation, this discovery, is more electrifying than anyone could have possibly imagined. It's giving answers and theatrics. Let's get into it. Our story actually begins in the simpler time of 1998. Brandy and Monica's hit song, The Boy Is Mine, is crushing hearts and airwaves, and Celine Dion's My Heart Will Go On is leaving audiences in fucking tears during a little film called Titanic. In all of this noise, researchers from the National Science Foundation were aiming its Very Large Array Radio telescope at the night sky. Some 4,000 light-years from Earth, the VLA picked up what the team described as a sun-like star. They noted the coordinates, and that was that. Well, just 2 years later, and with only 2 years of technological advancements, in the year 2000, this sun-like star was peeped upon once more, and wouldn't you know it, the team saw it was now donned with an accretion disk. Needless to say, when a star shows up to the party suddenly dressed with flair, you should keep an eye on it. From the year 2000 until 2002, that party raged, when suddenly the accretion disk disappeared, leaving astronomers with a sun-like star yet again, and now with even more questions as to what in the holy hell is going on in this part of the sky. Quote, "This strange behavior puzzled astronomers, and there were several different theories for what the object could really be," said Ingrid Stairs of the University of British Columbia in an interview with ScienceNews.com. That mystery raged for 5 years until 2007, when the National Science Foundation's Robert C. Byrd Greenbank Telescope in West Virginia said, "Y'all, you're not going to believe this, but that's not a single star. It's a binary system. And the stars are so close, they orbit one another every 4.7 hours, which is why it was mistaken for a single star. Oh, and by the way, one star is a quarter the size of our sun, and the other is a millisecond pulsar spinning 592 times per second. I thought you should know. Okay, I love you, bye. Yeah, my friends, this was a binary system all along, half of which is a newly minted millisecond pulsar dubbed PSR J10230038, or simply J10 for the purposes of this episode. And it's spinning, like a lot, at a rate of 35,520 times a minute. But good news, that nauseating spin is not the most surprising thing. There are 2 other surprising things. 1, now confirmed as a pulsar, this is the first ever sighting of such a neutron star with an accretion disk. Such a sighting means it's stealing and accumulating supplies from its buddy. Again, this has never been documented previously. And 2, it looks as though J10 likes to have options when it comes to popping off. Back in ye old 2009, Anne Archibald of McGill University in Montreal and her colleagues published a study on our pulsar after giving it a thorough, and I mean thorough, examination. They used ye old Robert C. Byrd Green Bank Telescope, the Westerbork Radio Telescope in the Netherlands, the Arecibo Radio Telescope in Puerto Rico, and the Parkes Radio Telescope in Australia. After all was said and done, no one was expecting these readings. When J10 lacks its accretion disk, it acts like any other pulsar, sending radio waves out from either of its ends. I mean poles. However, as material builds and that accretion disk reappears, J10 goes radio silent and emits X-rays. X-rays, and to put how truly wild this is into perspective, radio waves and X-rays are on total opposite ends of the electromagnetic spectrum, with radio waves at the low-frequency, long wavelength end, and X-rays at the high-frequency, short wavelength end. Also, side note, as of the release date of this episode, J10 is only one of 3 known pulsars who act this way. So it belongs to a brand new subcategory called transitional millisecond pulsars. J10 is the uniquest of the unique when it comes to stellar bodies. So, you guessed it. Researchers are asking, why the fuck and how the fuck can J10 do this? The answer would take nearly 2 decades and a nerdy village. So please, join me, will you, now in 2025, along with an international team of astronomers based in the US, Italy, and Spain, and whose collective brainpower was combined with the observations from NASA's IXPE, or Imaging X-ray Polarimetry Explorer, nailed it, the only telescope capable of measuring the angle of polarization in both X-ray and optical light. Now, I can see your reaction from here, and I think you're thinking, that's cool, but what the fuck is polarization? And why did they decide to use this particular doohickey? Great questions. Polarization is basically a fancy way of saying light or energy that is oscillating or moving as a wave towards a specific direction, in a defined path, if you will. And because of that, you can measure it using angles. An example of polarized energy could be light that bounces off a surface, like water, a road, or an electromagnetic field. Put a pin in this. Unpolarized light, like that from a burning fire, for example, has electric field vibrations in all directions, and that's harder to measure with angles. Maria Cristina Baglio of the Italian National Institute of Astrophysics Brera Observatory in Marate, Italy, and lead author of the paper we're shimmying into right now, and her colleagues chose this instrument to see how organized J10's X-rays were. They then compared and contrasted this reading to those from NASA's NICER, or Neutron Star Interior Composition Explorer, Neil Gehrels Swift Observatory, and the European Southern Observatory's Very Large Telescope in Chile, which focuses on the polarization of visible light, another form of energy released by J10. I am out of breath, and I told you it took a village. So, after all the nerding out and clickety-clack calculations were made, what did the team find? Drumroll, please. Thank you in the back. My friends, brace yourself. It turns out, wind isn't only made of air. As reported by the website sci.esa.int, quote, according to the new model, the pulsar emits a strong electromagnetic wind, which then interacts with the accretion disk around the system. As this wind hits matter in the accretion disk, it creates a massive shock, which accelerates the electrons in the wind to extremely high speeds. The electrons then interact with the wind's magnetic field, producing powerful beams of accelerated radiation that can be observed in light and X-ray bands at the same time. End quote. So, these X-rays are formed not from J10 itself, but from what's called pulsar wind, a flow of high-energy particles and magnetic fields that stretch into that accretion disk of stolen goods. It's their interaction that causes this radiation and blocks radio waves from getting out. When all that material is booted into the great beyond, those radio waves are free to emit once more. There's a handy-dandy illustration over at the socials depicting this scene. J10 is in white and popping off a white electric field. Its neighbor is in red, and so is the accretion disk swirling our little thief. The red parts interact with the white parts, and bada bing. You got yourself X-rays as an end result. It took some time to figure that out, but I think it's totally worth it. And thank you for listening, rating, subscribing, following, telling your friends about the new monster black hole that's 36 billion times the mass of our sun. I don't know what you do with that number. I don't know. Just drop it in a conversation and tell them Happy New Year. That something like this out there exists. And that pulsar too. That's too much. Everything is too much. God, an electric thanks to the folks over at Airwave Media, the podcast network to which WTI belongs. If you love this show, and you do, you love the other podcasts in this family. And please, stay interesting.